Just check if the SPSS screen is visible.
Yes, sir.
Yes, sir.
The copy.
Yes, sir.
Yes, sir.
Okay. And the slides also.
Yes.
Okay. I would like to thank AK Das Gupta Center for Planning and Development for giving me this opportunity. Today, our topic is testing of hypothesis and normality test. Now, we, the people of social science, use SPSS as a tool for our research and for our analysis. So, I would like to keep the presentation as simple as possible without much going into statistical jargons. Only that much that is required for us we shall cover, and we shall see using SPSS how the different testing of hypothesis is done. So as the topic name says, testing of hypothesis, what basically is hypothesis? Well, hypothesis is an assumption about the population parameter. Simply, if we say that hypothesis is basically an idea that needs to be tested based on available evidence. Say I say smoking leads to lung cancer. It's an idea. It's a statement. Basically, it's an hypothesis that needs to be tested and to prove that this statement is credible or not. Or we say the average weight of this class is 60 kg. It's a hypothesis. It's a statement that needs to be further tested and to decide whether that hypothesis is credible or not. So the definition says that a hypothesis is an assumption about the population parameter. So what is parameter? Parameter is a characteristics of population like mean or variance. In statistics, population parameter is generally a number that describes something about the entire group or population. Say, we say that the average weight of this class is 60 kg. So this 60 kg average is the mean weight of the class that describes that the average weight of the class is 60 kg. Now, we have said that hypothesis is an assumption about the population parameter which needs to be tested. How shall we test it? It's pretty simple. We need to collect some data, then we need to calculate some statistic and use that information to judge whether that value of the population parameter is correct or not. Well, I used to see that when my grandmother used to cook the rice, she used to take one or two rice from that pot, just press it, and she used to form an opinion whether that rice has been properly boiled or not. So what basically she was doing a hypothesis testing. That entire pot of rice is the population. From that population, she has picked up 5 or 6 rice, that is the sample. She has tested that sample, she has pressed those few rices and seen whether it has been boiled or not. And from that sample, she is making a decision whether that entire pot of rice is properly cooked or not. That is what we will do in hypothesis testing. From that population, that is the entire thing, we shall pick up a sample. We shall calculate some sample statistic. We shall test it, and based on that sample statistic, we shall comment on the entire population. So this is what we will do in hypothesis testing. The entire thing is the population. From that, whatever we draw, that is the sample, we will compute some statistics, which may be mean, which may be a proportion, depending on the thing we are testing. And then based on that sample mean or proportion, we shall comment on the population mean or population proportion. So the sample which we take, that represents the entire data. So that's what we have said, that we will collect the sample data then calculate some statistics and use that information to decide whether that the hypothesized value of the population parameter is correct or not. To test the validity of the hypothetical value of a population, we shall gather the sample data and determine whether the difference between the hypothesized value and the sample value. We shall judge whether the difference is significant or not. Later on, with an example, we will see how it is to be done. So we have a hypothesis, we have a hypothetical value. We will take some sample, we will collect, we will calculate the value from that sample, and then we will see whether that sample value and the hypothesized value, whether there is significant difference or not. If the difference is small, then it is the chance that the hypothesized value that we have taken is correct. If the difference is large, then there is a chance that the hypothesized value that we have taken, more chance that the hypothesized value that we have taken is not correct. So the first step of hypothesis testing is to state the hypothesized value of the population parameter. In this, we start with an assumption. That assumption which we start, that we call it null hypothesis, denoted by H0. Say we say the average weight of this class is 60 kg. So this is our hypothesis. This is our null hypothesis. We are assuming that the average weight of this class is 60 kg. So the null hypothesis is denoted by H0. So the average weight of the class is 58 kg. So we shall start with the assumption that the null hypothesis is true. Now, against every null hypothesis, there is an alternative hypothesis which is denoted by H1. So this is opposite of the null hypothesis. So if our null hypothesis is that the average weight of this class is 58 kg, the alternative hypothesis will be the average weight of this class is not equal to 58 kg. So this is the alternative hypothesis that is denoted by H1. So when we start with the hypothesis testing, first we will form the null hypothesis. Against that, we will form one alternative hypothesis. Now, this is the procedure. First, we will set up the hypothesis. Next is we will set up a suitable significance level. Now, what is significance level? So significance level, it's basically the confidence with which an experiment is accepted or rejected. That is the significance level. In our test, generally we take 1% or 5% as the level of significance. 5% level of significance means that out of 100, there is 5% chance that we would reject our null hypothesis, or in other words, that there is 95% chance that our null hypothesis that we have taken, it is true, that is correct. So we have started with the null hypothesis that the average weight of this class is 58 kg. So if we take the significance level at 95%, then we say that there is 95% chance that the average weight of this class will be 58 kg. Or if we take the significance level as 1%, then we will say that there is 99% chance that the average weight of this class is 58 kg. So 1% chance is there of rejection. Now, this graphically is represented with the normal curve. So if our significance level is 95%, if we are taking the significance level of 5%, then this white region is that 95% area where the null hypothesis will be accepted. And this shaded region is the rejection area, that 5% area. If the value falls in the shaded region, then we will say that our null hypothesis is not accepted. So first step is to set up a hypothesis, H0 and H1. Second step is to determine a significant level. The significant level that is generally denoted by alpha. 5%, 1%, 5%, and 10% people generally work with. As a standard, 5% is a good choice. Now, if that's what we have said, that if our sample statistic, that the value which we calculated have fallen in this shaded region, then there is, if it falls in the non-shaded region, that is the white region, then the null hypothesis is accepted. So whatever hypothesis we have taken, that is correct. And if it falls in this shaded region, then the null hypothesis is rejected and we accept the alternative hypothesis. The third step after setting up the hypothesis and determining the significance level will be to determine the suitable test statistics. That may be t-test, z-test, chi-square test, or f-test. That we will talk about that later on, which test statistics to select. Then we will determine the critical value from the table. That also, along with the example, we will see how that from the table we will determine the critical value. We will compute some value and we will compare it with the tabulated value and make the decision. When I will be taking the example step by step, I will come back to all these things. The decision is, if the computed value is more than the tabulated value, then it falls in the critical region and the null hypothesis is rejected, or else it is accepted. So this is how it looks like. First, we will formulate the H0 and H1. Then we will choose the level of significance. We will determine the appropriate test and then calculate the test statistic. Now, the test statistics, what we have discussed so far, there will be a tabulated value, and if our calculated value is more than this tabulated value, then the null hypothesis is rejected. Alternatively, there is a way of checking by way of the probability. Say, if we have taken 95%, say we have taken 5% level of significance, that means there is 5% chance that the null hypothesis will be rejected. So if the probability associated with the test statistics is less than 5%, then we will reject it or else accept it. This we will see with the help of the example, and we will draw conclusions accordingly. So this is what is done in hypothesis testing: formulation of the hypothesis, determination of the test to be done, choosing the level of significance, comparing the calculated value with the tabulated value, or comparing the probability associated with the test statistics with the significance level, and to either accept or reject the hypothesis and draw necessary conclusions. Whether we go with this one or we go with this one, the result will be same. For working simplicity, people generally go with the probability side. We will see both when we will be taking up examples. Now, in doing this hypothesis testing, we generally come across 4 situations. One situation is when the H0 or the which we have taken is true and our test accepts it. Average weight of this class is 58 kg. This is our null hypothesis. This is actually true, and the test also gives me the same result. Well and good. There can be another case. We say that H0 is 58 kg, but actually H0 is not 58 kg. The average weight of this class is not 58 kg. So the H0 is false and the test result rejects our null hypothesis. That is also correct. But if we come across this case that H0 is true, but the test rejects it, the null hypothesis which we have taken, that is actually correct, but the statistical test rejects our null hypothesis, then this sort of case is known as type 1 error. An alternative to it, there can be another situation when the null hypothesis actually is false, but the statistical test results which we get, that accepts that result, that accepts the null hypothesis, though that is not true, but still it is accepted. That is known as type 2 error. Say in a courtroom, this is a very common example given: courtroom trial. In a courtroom, the defendant is considered not guilty unless he is proven to be guilty. So the null hypothesis is the defendant is not guilty. Alternative hypothesis will be the defendant is guilty. So think of this situation. Actually, the defendant is not guilty. The judge has given the decision, right decision, correct. Actually, the defendant was guilty. Our hypothesis was defendant is not guilty, but actually the defendant was guilty and the null hypothesis was rejected. That is also a right decision. But you think of a case where the defendant is actually not guilty, but the court decision came that the defendant is guilty. So actually he is not guilty, but the decision rejects our null hypothesis. Then that is a case of type 1 error. And another is, in reality, the defendant is guilty, but the null hypothesis is accepted. That means the judge has said that he is not guilty. The null hypothesis holds. So that is a case of type 2 error. So in case of hypothesis testing, we can come at the decision that we can reach can be prone to these two type of errors: type 1 error and type 2 error. Type 1 error is when the null hypothesis is actually true, but it is rejected by the statistical test. And type 2 error is when the null hypothesis is not actually true, but the statistical test accepts the null hypothesis. Up till now, are you with me? It's clear? Anything to be said?
It's clear, sir.
Okay. So basically, the main difference why type 1 error and type 2 error comes is choosing of the significance level. Say, if the significance level set is too lenient, say I have taken, instead of 5%, I have taken a significance level of say 15%, a high significance level. That time type 1 error comes. And when I take too lenient a significance level, say 1%, a too stringent a significant level, say 1%, in that case, the type 2 error comes. So generally, this type 1 error and type 2 error, this comes because of the taking of the level of significance. Now, the level of significance influences our decision. It is who determine the level of significance. So it is based on our decision, this type 1 error or this type 2 error that will come. Another term that is associated with testing, hypothesis testing, is one-tail test and two-tail test. Say, we say the mean is not equal to 10. So we can come a case where the mean may be more than 10 or a mean may be less than 10. So if our null hypothesis is mean is equal to 10 and alternative hypothesis is mean is not equal to 10. So if a mean more than 10 also, the null hypothesis will be rejected. A mean less than 10 also, the null hypothesis will be rejected. That is a case of a two-tailed test. So this can be both on the greater side as well as on the lesser side. The null hypothesis can be rejected. But if it comes on the one side, we say that the mean will not be more than 10, but the mean comes to 11 or more than 10. So that is a right-tailed. Or we say the mean will not be less than 10. The mean comes to 9 or 8. So on the lesser side. So that is also a one-tailed test. So a one-tailed test is when it comes under one side, and a two-tailed test is when it comes off both the sides of this curve. Hypothesis testing basically are of two types. The tests are of two types. One, it is the parametric test. Another is non-parametric test. Now, Parametric test, it relies on the theoretical distribution of the test statistics under the null hypothesis. The assumption is that the distribution of the sample data, that is normal. And in case of non-parametric test, it is distribution free. There is no such assumption that the distribution of the data is normal. So the parametric test is applied when the data is normal, and the non-parametric is applied for other types of distribution. These are basically the types of tests: parametric, one sample test, two sample test, and the non-parametric test. Here we will mainly deal with the parametric test. Parametric test, one sample, it can be T test and Z test, and two samples, it can be group 2 test, Z test, paired T test, and if there are more than two samples, then there can be test of ANOVA. We shall see all this test here. We shall start with T distribution. Now, parametric test says that the distribution will be more or less normal. So the condition of normality should hold. Now, T distribution, it is generally applied when the T test is generally applied when the sample size is small. Say sample size of less than 30. If we are dealing with a sample size of less than 30, we apply the T test. The T distribution is generally, it's similar to the normal distribution with an added parameter called the degree of freedom. When we will be using the T test, we will use this degree of freedom. Now, what is basically degree of freedom? Degree of freedom is said number of observations n minus 1. Just let me take a simple example. Say I have 7 shirts and I have 7 days, Monday to Sunday to next Saturday. So every day I can wear one shirt, and the one shirt which I wear, I will not use it next day. So on Sunday, I have one shirt, I use one shirt. So the choice that was left with me was 6. I could have taken 6 other shirts. On Monday and Sunday, one shirt is already used. I have chosen one shirt. How many choice I have left with 5 shirts left? On Tuesday, 2 shirts gone. If I will wear one shirt, I have got the choice of 4 more shirts to choose from. This way, in the last day, only one shirt is left. I have nothing to choose from. This is how the degree of freedom works. It is n minus 1. The choice, the number of distribution minus 1. When are the t-test applied? T-test may be applied for a one sample test. One sample test means, say, if a car manufacturer says that the car will give a mileage of 20 on an average, a certain brand of car will give a mileage of 20 kilometers per liter an average. We take 10 cars, 15 cars and test the mileage and determine whether the claim is true or not. So in that case, we will use the one sample test. To validate some claim, we will take a small sample, we will test on it, and then we will comment whether the claim is correct or not. Two sample test, it is applied to compare the difference between the average difference between whether there is significant difference between two groups or not. Say there are two brands of pizza company and they are delivering it within, say, both are claiming we will deliver it within 15 minutes. Now we will check and see whether there is significant difference between their claim or not, or whether their claim is correct or not. That is a two sample test. And the third one is a paired or t-test, or compare two paired groups. Say Before taking tuition, this was the result. After taking tuition, this is the result. Without using fertilizer, this is the output. After using fertilizer, this is the output. Now, whether taking the tuition has a significant effect on the marks of the student, or whether using fertilizer will have, using that brand of fertilizer will have significant impact on the production of the crop or not, that those type of situation, we use the paired t-test. So what is the key difference between t-test and z-test? We have said that here in the parametric test, we have said that t-test, we have talked about t-test and z-test, whether on a single sample or on a group or on a paired basis. So what is the main difference between t-test and the z-test? Basically, the difference is if the sample size is less than 30, we use the t-test. And if the sample size is large, that is more than 30, we take the z-test. So t-test, it is used to compare and analyze the basically the mean of two population from or one or group when the standard deviation is not known. As against z test, it is applied when the standard deviation is known. Basic is when the sample size, if it is less than 30, we will apply the t test. If it is more than 30, we will apply the z test. Now the t test, it is based on the two students t distribution, and z test relies on the sample mean is normal, but the t distribution also appears similar to the normal distribution. Let us take the t test. First was one sample t test. This is an example given to you. Just have a reading of that example. So the blood pressure of a normal male should not be, it should be about 129. So it should not be more than 129. So that is the claim. Now, a sample of 12 men were taken and their blood pressure count has been taken. So first we will see, we will compute at 95% confidence interval, that is at 5% level, the mean systolic pressure of the adult, that what should be the, within what range the blood pressure varies. And then at 1% significance level, that is at 99% confidence level, we shall see, we shall check whether this claim, that is the average blood pressure, should be around 129 or should not be more than 129, that we will test. Now, I have the SPSS here open with me. The data, I have saved it. This is the blood pressure of 12 males selected at random. So first the requirement was to check at 95% confidence level. Confidence level 95% means significance level of 5%. So 5% significance level, what is the mean range of the blood pressure. How to check the mean? We will go to analyze. Next, we will go to compare mean. This is a case of one sample test. We shall click the one sample test. I have given the variable name as blood pressure BP. So this is the only variable here available. We will click and transfer it as the test variable. Once the test variable is selected, we shall go to option. Our level of confidence is 95%. That is, the significance level is 5%. So by default, the confidence level is given here is 95%. Suppose our confidence, if we wanted to test it at 99%, we would have changed that to 99. So here the confidence level is 95%. So continue and press OK. We get this result. Now, how to interpret this result? In this one sample test, come to this 95% confidence interval of difference. This is the lower bound and this is the upper bound. So we can comment from here that we are 95% confident that the blood pressure of the adult male of this area will be somewhere between 124.14 to 141.186, 141.86. So this is the range in which the blood pressure will vary of the adult male of that area. So this decision we are taking with 95% confidence based on a small sample of 12. So, this is not an hypothesis testing. This is just the range, how to calculate the range. Next comes the testing at 1% significance level, the suspicion regarding the blood pressure of this community. So here, the normal male is supposed to be about 129. So the blood pressure, a lower blood pressure of 129, it's very much acceptable. So the blood pressure should not be more than 129. So basically, this is a one-tail test on the more than 129. So it is a right one-tail test. So there should be some hypothesis. What should be the hypothesis here? The null hypothesis is H0 mu, the average, is 129. This is the first step. Against this, we have an alternative hypothesis that the mu will be more than 129. Acceptable range is up to 129, but more than 120, the claim is that the average blood pressure should be around 129. So more than 129, that is the alternative hypothesis, which is opposite of the null hypothesis. This is the and our significance level 1%, that is 0.01. At 1% we will do. Now just let us go back to the steps. Step 1, set up a hypothesis. Step 2, set up a suitable significance level. Step 3, determine a suitable test statistics. So here we have followed step 1. We have formulated the hypothesis. Next, we have determined the significance level. Next, we will develop a suitable test statistics. In this case, it is a small sample, so this will be a t-test, so that we will determine. How to determine? Let's go to SPSS. We go to analyze, compare mean, one sample test. Now, since in the last example, we have taken blood pressure, so it is already selected. Otherwise, it will look like this. We will take it as the test variable. The test value here is 129. So the null hypothesis is 129. So this is the test value. Let us go to the option. So by default, it is selected 95%, but our problem says that at 1% significance level, so confidence interval of 99%. So change this to 99, continue, and let us click OK. This is the output here. So what is the value here? The value of t here, it is 0.994 and degree of freedom is 11. We had 12 observations. So the degree of freedom here is 11. Now, how to take the decision? Just let me go back to the slide once more. Setting up of the hypothesis, setting up of the significance level, determination of the suitable test statistics. So we have determined T statistic. Now is to determine the critical value from the table. After doing the computation, check with the sample results and make necessary decision and take necessary decision. That we will be seeing here. Our T value here, it is 0.994. This is the T value, 0.994. Now, we will compare it with the tabulated value. Now, there is something like this, a T table. Now, what is the tabulated value? We are checking it at 1% level. 1% level is 0.01. So this is one-tailed test, 1% level. The second one is two-tailed test. For two-tailed test, this column is the for two-tailed test, this column is the 1% level. For one-tailed test, this column. So this is a one-tailed test, 0.01. Degree of freedom is 11. Let us come down. Degree of freedom 11. The value is 2.718 or 2.72 approx. So here our T value calculated was 0.944 and the tabulated value T here is 2.72. So 2.72 is the tabulated value. Now, since our computed value, if the computed value is more than the tabulated value, we will reject the null hypothesis. So the computed value is this one, and this is the tabulated value from the table we have found. It is 2.72. That was the tabulated value. So here the computed value is less than the tabulated value, and therefore H0 is accepted. Had that computed value been more than the tabulated value, so in that case, the H0 would not have been accepted. So we can comment here that there is not enough evidence to conclude that the blood pressure of that community will be more than 129. So this is how the testing is done. First step, selection of the hypothesis. Second step, selection of the significance level. Third, to compute suitable test statistics. Then to get the tabulated value, compare the computed value with the tabulated value, and make necessary decision. This is what we have shown in our slides. Determine the suitable test statistics. Third step, determine the critical value from the table. Check the result and compare it with the tabulated value and make necessary decision. If the computed value is more than the tabulated value, then it falls in the critical region. In that case, the null hypothesis is rejected. Otherwise, accept. In our case, the computed value is not more than the tabulated value. So we will cannot reject the null hypothesis. We will accept it. So this is one way of testing the hypothesis. We have gone through this right hand side method, that we have computed the t-test, and we have taken the critical value, and we have compared it with the table value, and we have made the decision. Another way is to determine with the help of the p-value or the probability value. Now, what is the probability here? Let us go to the result. The probability here is under significance, 0.342. So p-value this p-value is 0.342. But you see, this is the case of 3.342 is the case of a two-tailed test. But in our case, this is a one-tailed test. So for a single-tailed test, the p-value that we will take is, we will divide this by 2. That is 171. This is the p-value. And what is the acceptable, what was our level of significance? Our level of significance was 1%. Now here, if this p-value here is less than 0.01, then the null hypothesis will be rejected. But in this case, the p-value is more than 0.01. The p-value is 0.171. So we accept the null hypothesis. So same decision, it is, we have come through this probability side. So if in case of probability, we will compare the probability of the t statistics with the level of significance. If it is less than the level of significance, we will reject the null hypothesis. If it is more than the level of significance, we will accept the null hypothesis. And here we will compare the we will compare the computed value with the tabulated value. If the computed value is more than the tabulated value, the null hypothesis will be rejected, or else it will be accepted. So whichever way you go, you will get the same result. Is this example clear? Okay. This was an example of a one sample t-test. Next, we will see a two sample t-test. There is an example given. Just read that example once. So this is basically the pollution index of two areas in a city. There are 8 observations. Now, the hypothesis is the mean pollution index of the two area are same. So from one area, 8 pollution data has been collected, from another area also of the same city. 8 samples has been taken. At 5% level, we need to check whether the mean pollution index of both these two areas are same or not. So this example, we have compiled the data in SPSS. First is area A, the pollution figures, and area B. Now, before we proceed, we must number this area A, area B. We must give some number, A to be denoted by 1 and B to be denoted by 2. We must code this area first. So coding, how it is done? So area, it is already, I have already made the code here. Suppose there was another area. So that value, area C, that value will be given as 3. I add this. How to add? In this value, here we will click, we will get this, the value and the level, that is the name. So if I go to the data view here, I write 1, that automatically will be area A. I write 3, that automatically will be area C, which I have created just now. Let me clear off those extra. So when we are proceeding with the two samples test, first we need to code our data. So this is the index and that is the area. The area, those are not numerical figures. So we have to make SPSS understand it. So we are giving code 1 for one area, 2 for the other one. So how we will proceed? We will go to before we proceed, let us develop the hypothesis. Hypothesis is the average population index of both the area is same. This is one way of writing mu A is equal to mu B. Some people write it this way, mu A minus mu B is equal to 0. Whichever way you write, that is same. Against this, the alternative hypothesis is the mean of the pollution index is not same. Or we can write it this way. Whatever way we want, we write. This is the first step. Next step is to determine the significance level. As per this problem, the significance level is 5%. So 0.05. Now we will go to the testing. We will calculate the t statistics. So we will go to analyze, compare mean, independent sample t-test. We will select. This box opens. The test variable is the population in a pollution index. So select index, transfer it as the test variable, and the area as the grouping variable. So select area and make it as the grouping variable. Go to option. It is 95%. That 95%, it is already 5% level of significance. 95 it is chosen. And in this area, we will define the group. Group A, we have coded it as 1. And group B, that is the second one, we have coded it as 2. So we will write 1 and 2, continue. Once this is done, click OK. This is the result. Just let us first simply make the decision based on the probability. What is the probability of the test statistic? The probability of the test statistic here is 0.162. So p-value is 0.162. And the level of significance, that is alpha, is 0.05. So if it was less than 0.05, the null hypothesis would have been rejected. But since the p-value is more than alpha, we accept the null hypothesis. So we accept the null hypothesis and we compute. There is no average difference in the pollution index of the two area. This can be one way of deciding, and another way is through going through the T tables. So what is the T value that we have obtained from here? We have obtained a T value here is 1.487 for 14 degree of freedom. So let us go to the T table. We were doing the test at 5% level, 0.05, and this is a two-tailed test. So under two-tailed, we will come to 0.05. The degree of freedom here is 14. So let 0.05, let's go to 14. So the value, the T value will be 2 point T by 14, 2.145. Now, since the computed value is less than the tabulated value, the null hypothesis is accepted. Now, if this computed value was more than the tabulated value, then the null hypothesis would have been rejected. So whichever way you go, either through the probability or through the comparing the calculated value with the tabulated value, we will come to the same result. The first case was the case of one sample test, and this is a two sample test. So this is how the testing is done in SPSS. Now, we have said that parametric test, the data follows the assumption of normality. Now, how to check whether the data is normal or not? We can either construct a histogram and to check whether it's normal or not, or we can just use these statistical tests, the Sapir-Whorf test or the Kolmogorov-Simon test. They will tell us whether the data is normal or not. In this test, the null hypothesis is that the variable is normally distributed. An alternative hypothesis is it is normal, it's not normally distributed. Same way, we will compare the p-value with the level of significance. And if the p-value is less than the level of significance, we will reject the null hypothesis or else we will accept it. Let's check. The first example which we have taken, this was the sample.
Sir has taken a break or he was disconnected.
So I think it got disconnected.
You got the disconnected.
Yes, yes, I am calling.
Sir has joined.
Yes, yes. Now he realized that he was.
Oh, sorry, I'm hello, hello.
হ্যাঁ হ্যাঁ হ্যাঁ
হ্যাঁ
জয়েন
স্যার
হয়েছে স্যার
শোনা
ডিসকানেক্ট
যাচ্ছে?
হ্যাঁ হ্যাঁ
হ্যাঁ স্যার
সরি,
sorry,
আমার ইয়ে হয়ে গেছে।
disconnected.
জাস্ট 2 মিনিট হয়েছিল
ওকে, ওকে। So let me take the first example. This was the data. We were talking about normality. I think normality, that portion was, I was there with you when I was talking about the normality.
So till you had shown the slide where we could use histograms or we could use the tests, and then you started conducting the tests, sir, and when you got disconnected.
Okay, okay. So this is the first example which we were used, which we have been using. So this was the sample. Now we will go to descriptives and then explore. This is the data here. We transfer it to this dependent and then we go to plot. In this plot, we shall select the histogram and we shall select the normality plot with test. I repeat once again. So this is the data, first data. We will select analyze, go to descriptives, explore, select the data here under plot. By default, it is given stem and leaf. You undo it. You can keep it there, but then we will have lots of output. We require the histogram and normality with the test plot. Continue. Okay. See, more or less from the histogram, it's more or less a normal distribution. But this statistical test here you see the significance level, it is more than 0.05. Both the tests, it is more than 0.05. Our null hypothesis is that the data is normally distributed. Now, since it is more than 0, the result is more than 0.05, we cannot reject the null hypothesis. So we can say that the data is normally distributed, or the data follows normality. If it was less than 0.05, then the data wouldn't have been normally distributed. So this is how we check the normality of the data. Either it can be, you can use the histogram, or you can use this test of normality. So likewise, any data set can be used to test the normality. So we have taken one sample t-test. Next, we have taken two sample t-test. Next, we will do the paired t-test by using the same data that we have used for the second example, two sample test. In two sample test, the data was pollution index of two areas of a city. But here, this same example, it's slightly, we can modify it. That is the pollution index from two area in a city on a same day. That means, say on January 1, this is A area, this is B area. January 2, A area, B area. January 30, A area, B area. So there is a pairing. So that is for the same day. This is the area A data and this is the area B data. In this case, there was no such restriction. Some 8 observations were taken from area A and some 8 observations were taken from some area B. And we were commenting whether there is a significant difference in the mean pollution index. So here also, we will see that we will reanalyze whether there is significant difference in the mean pollution index of the both the area, but the data, it is slightly modified. That is, it is a paired data. That is day 1, this is the pollution of area A, this is the pollution of area B. Day 2, this is the pollution of area A, this is the pollution of area B, and so on. So how to go with the paired test? So the same data we have organized it as area A and area B. First variable is area A. The second one is area B. Next, we need to calculate the difference. Transform compute variable. It is area A minus area B. It can be B minus A also. And the target variable, let's call it the difference. This we go from the transform compute variable, this command. Okay. Now we have created another variable, that is the difference. Now this case only we have been able to create this because this is a paired data. For day 1, this is the data of area A and B. For day 2, area A and B. So we will comment whether there is a significant difference in the mean pollution of both the area. So first, we will compute the difference. Next, go to analyze. Compare mean, paired t-test. Area A and area B, you take together and transfer it here. Once this is done, let us click on the option, and in this problem the level of significance was 5%. So level of significance 5%, it is okay. Continue. Okay. Click OK. Check the significance. The confidence, the level of acceptance is 0.05. It is less than the alpha 0.05. Now, since the probability of significance is less than 0.05, we will reject the null hypothesis and we comment that there is significant difference in the mean pollution index of the two area. So this is one way of going with the paired data. Another way of getting the same result is you go to, we have computed the difference here. Go to analyze, compute mean, and go with one sample test. Select the difference here. Since it is at 5% already selected, okay. You see, we have got the same result. 0 t-value is, you can go with the tabulated value also, but let's not waste time. So the significance level, it is 0.000. You click on it. Okay. So this is the, so it is less than 0.05. So we reject the null hypothesis and we comment that there is significant difference in the mean pollution index of both the area. Now the thing is, when we are using a paired data, we can go with either of the way. In the first case, we can use the paired test. We have used the paired t-test, and in the second case we have computed the difference, and using the difference as a single one, we have used the one sample t-test. Whichever way you go for a paired data, you will get the same result. Let us take another example from this paired data. This is the marks of 20 students, one before taking coaching, another one is post taking a coaching of a module. How to, whether there is, now the question is whether there is significant difference of the coaching, significant effect of the coaching on the marks of the students. Let us transform the variable, compute. In the last case, we have taken a minus b. In this case, after taking the coaching, most likely the marks will increase. So we are using b minus a. The target variable is same, difference. Sorry. We have the difference in the marks pre and post coaching. So you apply the test, go to the compare mean, one sample test, use difference. Let us test it at 5% level only, which is by default given. Okay. So here it's the value. It is 0.04 less than 0.05. The null hypothesis is rejected. So the null hypothesis will be there is no significant difference in coaching on the marks. The alternative hypothesis is no, coaching has increased the marks of the student. So this is a case of paired t-test. Paired t-test may be applied when we are having the data from the same thing, pre or post something, or on a single day for different area. So that is where we apply the paired t-test. So this is, we have so far covered the one sample t-test, two sample t-test and the paired test, this, and this. Next, we will move to the Z test. Z test is applied when the number of observations is more than 30. Now, in SPSS, there is no direct way of of using the Z test. There is no such command. So we will just use a backward method to get the Z test. Let us take another example. One proportion Z test. Let's just check the example once. The company claims that 20% of its customer drinks another brand. But out of a sample of 100 taken, it was found that 18 was drinking another brand. Now, from this sample, we will have to check whether the claim is correct or not. Out of 100, 18, sample of 100, 18 drinks another brand, but the claim of the company is 20% of the customer drinks another brand. So level of significance is 5%. So total data was for 100 customers. Out of that, 18 customers had other brand. So the remaining customers, that is 100 minus 18, that is the remaining 82 customers will have used the same brand. Now, we need to check whether the claim of the company that 20% of the customer use other brand, that is correct or not. So here also, the variable needs to be coded. So here it is the brand, the names are given, other, same. So we have to give numerical value that is already done. For other, the value given is 1. For same, the value given is 2. Coding same way that we have discussed earlier. So first, the brands needs to be coded. Next, what we shall do? We shall select data. Go to weight cases. Select count. Weight cases. Select this weight cases by count. So this brand A and B, we are going with the count. Once it is done, click OK. Next, go to Analyze. Under Analyze, in compare mean, you see we have only the t-test. The z-test, it's not there. So we will go to the non-parametric test. Though we are doing a parametric test, that is Z test, but since Z test option is not given in SPSS, this is how we will use the non-parametric test to calculate the Z test statistic. So under non-parametric test, you will find the chi-square test. Select chi-square test. The test variable is the brand, and in the value, the claim is that 20% drinks other brand. First 0.2, then the next one, the same brand, they number 2, they take 0.8, add. So for other brand, the percentage, the claim is 0.2, and for the same brand, the claim is 0.8. Once done, press OK. Now here we have got the chi-square value. The chi-square value is 0.25. Now from this chi-square, we will get the Z value. Z is root over chi-square. So here chi-square value was 0.25. So the Z value will be 0.5. Now, once you get the Z value as 0.5, now you compare it with the table. This is the Z table. Now, what kind of test is this one? Is this a two-tail test or a one-tail test? First, we have to decide that. So here, let us write the assumptions, a hypothesis. The claim is that 20% of them 20% of them drinks other brand. So the certain software bottler claims that less than 20% of the customer drinks another brand. So the alternative hypothesis will be H1 says that so 20% of them drinks other brand, but the alternative hypothesis is opposite to that, less than 20%. Now this is a case of which test? This is a case of left tail test, left. So this value, that Z we have calculated, we will put it as a minus value. Now if it was a right tail test, say suppose it was by greater than 20%, then we would have taken a positive value here. So this sign we have to assign depending on the, in case of one tail test, depending on the type of the test. So this is our left tail test, so minus 0.5. We will go to the table. 0.05 for one tail test. The value is value is minus 1.645. So the computed value is greater than the tabulated value. Minus zero point 0.5 is greater than minus 1.645. So the computed value is greater than the tabulated value, and therefore we reject the null hypothesis and the claim of the company that at least 20% of them drinks another brand. So when we come to Z test, SPSS doesn't give us the option to have use Z test. So we will use the chi-square test, and the chi-square test statistics that we will get the root over, and that will give us the z-test score. So that z-test score, we will compare it with the z-table, and from the after comparing with the z-table, we will decide on whether the null hypothesis is accepted or rejected. Next, another large sample test. Just read the example. There are two machines. Machine A, in 280 runs, they have produced 15 defectives, while machine B, in 200 runs, they have produced 10 defectives. Now, the question they want to test, are both the machines same? Whether there is difference in the reliability of both the machine. Now, machine A, total 200 runs, of which 15 were defective. So the remaining ones were acceptable product, 265. For machine B, out of 200, 10 were defective. So the remaining 190 was acceptable product. Now, we have to comment on whether both the machines are equally likely. Whether does the result imply a difference in the reliability of both the machines? Are both the machines reliable? That is, so here you see you have machines, you have defect quality, defective and not defective, and we have count. This count is the numerical figures, the other twos are not. So machine, you have to first give value to that machine. Machine A, I have given 1, so 2 is machine B, and defective is 1. We are testing the defectives. Defective is 1, 2 is acceptable. So for here, 1 implies machine 1, 2 implies machine 2, 1 implies defective, 2 implies acceptable. This is the first thing we need to code the data. Then we will have to weight the data. Data weight case. Select weight by case, the count, transfer it there. Okay. Once we have done with this, go to Analyze, select Descriptive Statistics, and then Cross tab. Select the machine, transfer it to rows, then select the quality of the product, transfer it to column, click the statistic, you select chi-square as the statistic, click continue. Once we have selected this, we will press OK. Check here, chi-square value is 0.03. So Z value will be square root of 0.03. It is 0.173. This is the Z score. Now here, whether both the machines are reliable or not, the null hypothesis will be and the alternative hypothesis will be. So this is a basically a two-tailed test. Let's go to the table Z value. Two-tailed test at 1%, it is 2.58. So 2.58, and our calculated value was 1.73. So since the calculated value is less than the tabulated value, we accept the null hypothesis and we can comment that there is no difference in the reliability of both the machine. So though directly we cannot apply the Z test here, but through the backdoor method using chi-square, we can calculate the Z test both for one proportion as well as for two proportions. So these are the tests that we have covered. Z test, one sample, one proportion, and Z two samples also, t-test also, one sample, two sample, plus paired t-test. Now, for parametric, another test is there, that is the test of ANOVA. Now, test of ANOVA will be applied when the data set is more than the number of variables is more than 2. In the t-test, it was 1 or 2, same with z-test. But ANOVA will be used for testing when there are more than 2, 3 or 4. So it is basically a multiple two sample test. So from this, how we will use this one-way ANOVA? We will just straight away, we will take one example and see. This is a very standard example it is used. So a standard mice, that is the zigzag track. On a maze, the 5 mice were selected and left on the zigzag track, those maze, and the color of that maze door was different. One's red, green, and black. The time taken for the different maze by 5 mice were given. Now the question is, has the color of the door an effect on the time taken. Just read it once. 5 mice were randomly selected to be placed in a standard maze with different colored door. The time required to complete the maze, the zigzag track, that is the maze, the total time taken to complete. When the door color was red, this was the time. When the door color was green, this was the time. When the door color was black, this was the time. Now, the question is, at 1% level, has the door color a significant impact on the time? Now, here there is the variable is more than 2. So t-test and z-test will not work here. So we will use ANOVA here. Let's go to SPSS. Five mice. This is the red door. This is the time. This is the green door. This is the time taken. This is the black door. This is the time taken. Now, first, we have to code this. These are non-numeric figures. So we have coded here. It's already done. 1 given for red, 2 for green, 3 for black. We will select analyze. Next, we will go to compare mean and select one-way ANOVA. The time here, you take it under the dependent list. And the door color, you take it as the factor. After that, we will click this post hub. And from here, we will select Q key. Our level of significance is 1% as asked in this problem. So we change it to 1%. Continue. Select option. Select homogeneity of variance. Continue. Okay. Now, these are the results. We will interpret the result. First, let us check the significance. The significance here it is 0.00001 point something, so up to 3 plus 0.00, and this is our level of significance is 0.01. So this is less than the level of significance, so the null hypothesis is rejected. So there is significant difference, so there is significant impact on the color of the door on the time taken. The assumption, the null hypothesis was that there is no significant difference. There is no significant difference in the color of the door. So the H0 will be red equal to green equal to blue. There is no difference. And H1 at least one inequality, at least one different. So this was the null hypothesis. So at 1% level of significance, the null hypothesis is rejected. So we can comment that there is significant, the color of the door has significant impact on the time. Now we have chosen some other command also. Now here you see that black and red has been grouped under one and green has been taken as grouped separately. So we can say that green is having, so the green color door takes a longer time for the mice to complete the maze as compared to red and black. And that's why the null hypothesis was rejected. This is all we have from the parametric testing of hypothesis and normality of data. So if you have anything to add to this, please, you're welcome.
Hello.
Yes.
So may I ask now?
Yeah.
Sir, you have assigned a specific weight while doing analysis. Sir, I want to ask the one simple question that why we assign weight in any kind of statistical analysis.
Which example you are talking about?
When you were applying the Z test, you have assigned weight cases. You have given the command of weight cases. Hello.
Yes. Just a minute.
Okay, sir.
Yes. See, in this example that we are taking, which we have taken, there we were testing that whether the claim of that bottler was correct or not. The claim was 20% were drinking other brand. So now here, in this data, we had there see it was just a moment, it's not presenting. You see here, in this case, we were having two types of information. Numerical one, 118, which we are having, that is, they are not consuming. And the 82 we are having, that is consuming. Though it is count, but the data type is different. Unlike in the t-test, all were same data. So we were assigning weights that this 18, what is the claim? 20% claim that they will have other not consuming that product. So we have assigned that weight. And the remaining 80, they are consuming that data. So this 82, which count, that as per the claim is 80% of the weightage, and 18 the remaining 20% weightage. That's why the weight has been given, since those are count, but the count is of different. One is for one brand, another is for another brand. So we were assigning weights and giving value to them.
Okay, sir, I understood, but I'm just asking a general question about that why we assign weight in the statistical analysis.
Because here the counts here, say A or B, those data, though they are not equal. So the chance, there is 80% chance that this will be done, or there is, say, some percentage of chance that this will be done, another percentage of time that will be done. So the mean data that is taken using weights. So these are basically the frequency counts that are given.
Okay, sir.